Okay, good morning, good morning. Welcome back. I hope we had a great weekend. We start today on page 19. And while you guys are opening to page 19, let me start with the same question we started with first thing on Friday. How are we doing with the chain rule? 1 thumbs down. 2 thumbs up. All right, the thumbs up take it so far. Oh yeah. It can be hard to read when you have so many nested chain rules. All right. So Sam, what were you, could you share like a general, like, okay, so there comes a point, so like the beginning ones are more straightforward for you, but then there comes a point where it's just like, this is hard and, right. Um, how about just to kind of, it's a Monday morning, it's dreary out, let's just kind of do one chain rule warm-up problem just to sort of bring us back in here and work with each other on this. So if I asked you to find the derivative of the following, let's do something like x cubed minus x to the 5th. So check in with each other, see if you can use the chain rule to find the derivative of that thing. Okay, so what do we have for this one? What goes first? So the 5 comes down. All this stays exactly the same. New power. 4. Chain rule says what comes next? Derivative of the stuff with a big multiplication symbol. What's the derivative of the stuff? 3x squared minus 1. What's missing? Parentheses. That whole thing is the derivative of the stuff. Sam, is this in the easier section or the harder section? All right, so that's the easier section. So what if instead we were to try to make it look harder? Something like this. Let's try 9 raised to the, and then I'm going to give you a big old power up here. Move it up. So for folks just coming in, we're kind of warming back up with just a few more chain rule derivatives. What do we notice about this problem? Right, so we have a number to some stuff. And in particular, how does this problem relate to the previous problem? So that power is the original problem we had before, right? Sam, is this starting to head in the direction of the more complicated ones? Yeah. So here's why I wanted to give you this example. Let's go ahead and write down the derivative right now, but we're not going to do the whole thing. Y prime equals, I have a number to some stuff, like 2 to the x. Is that the power rule? It's not the power rule. So what do you do when you have a number to some stuff? I'll remind us of this rule up here. A to the x becomes natural log of a times a to the x. That was before chain rule. That was just our derivative for a number to the x. So it is that rule. So now it's 9 to some complicated things. So what do we do first? Copy that whole thing down. 9 to the x cubed minus x to the 5th. Yes? Times. Still doing the rest of this rule in blue. Natural log of what? 9. Times, and now in English, what does the chain rule say? Derivative of the stuff. But the good news is the derivative of the stuff is something we've already done. That was the whole first problem that you guys did. So again, I'll be lazy, but all of this goes right in there. The derivative of the stuff, the derivative of x cubed minus x to the 5th. It's a whole chain rule, and it's a whole chain rule that you did up above. So maybe this is a new tactic if the nested chain rules are giving you trouble, is just take a look at like the simplest, smallest piece you can find. So if you gave me this problem in purple, maybe I'd say, okay, forget about the 9, it's complicated. Just deal with the x cubed minus x to the 5th. That's something we did up above and something Sam said was in the easier section of the problems. and then say, okay, now I know what the derivative of all that stuff in the power is. Now can I bring it back and talk about 9 to that thing? And you kind of end up working the chain rule from the inside to the outside, which is okay, and just build your pieces until you have the final answer. Just okay? Okay. So again, I think we're on page 19. So open to page 19 if you're not there already. We'll take our look at the calendar. Today, October 15, we have our review of trig functions. So we're back in chapter 1. And this is to prepare us for Wednesday's class where we talk about the derivatives of the trig functions. Now, we actually have already talked about the derivatives of a few of the trig functions, but we just did it to give us another opportunity to practice chain rule. So we're going to kind of pretend we don't know any derivatives of sine or cosine or tangent, and we'll just start from scratch there on Wednesday. Coming up on Friday of this week, 2 things. Number 1, the project is due. Everybody has the project, right? Number 4. So the 4th project is due Friday, am I right? October 19. And also our 4th quiz is on Friday, October 19. Any questions on the calendar? Okay. So we'll come back to page 19. We'll start here at the bottom. And it says, first thing we're going to do before we reintroduce the trig functions is have a look at a sketchpad thing that's supposed to remind us of what the heck a radian is. So here is a sketchpad thing that I made up. So we're focusing on that angle. And at the moment, I want you to try to compare the length of the red, which is the radius, to the blue, which is an arc length. Blue there. So right now, which one do you think is bigger, red or blue? Red looks bigger. And if I change this angle, you can see that at some point, what's bigger? Blue is bigger than red. Okay, so fair enough, we're just comparing, and it's hard to think about the length of a curvy thing, but it's, you know, if you had a string, you could put it on the circle and then straighten it out and measure it on a ruler. So it's got a length, and someplace in between, what special thing happens? They're equal, right? If in the beginning the red was bigger, and then later on the blue was bigger, there must be some magical spot in the middle where they are equal. Okay, so I'm just eyeballing it. Does it look like maybe the blue and the red are approximately equal? In this case, you might think I'm off by a little bit, and I probably am. But that angle right there is a special angle. Do you know how we define that angle? That is 1 radian. The measure of that angle, if I've got it right, if the blue is equal to the red, the measure of that one angle that makes that happen is defined to be 1 radian. Degrees are a fairly arbitrary way to measure angles, and I know that probably we're all much more comfortable measuring angles in degrees than in radians. But all of calculus is done in radians. We'll see why next class. But anyway, 1 radian is that special angle where the arc is the same thing as the radius. So let me show you the measure of the angle in degrees. So right there, it's about 57 degrees. And I'll show you the measure of the radius is 5. Okay, so on the smartboard, it's obviously not 5 centimeters, but on the computer screen, it's 5 centimeters. And then I'll show you the arc length, and it's 4.98, which is darn close. So that angle right there is darn close to the magical one, which is 1 radian. Now, if that's 1 radian, can you tell me what should I try to do to this guy to make an angle that's 2 radians? I want to double it, right? So how much do we want the arc length to be if I want a 2 radian angle? I want it to be 10. So we'll swing this guy around and try to make that thing about 10. And maybe someplace around there. That bigger angle is 2 radians. And so we start to think about, I'll write it here on the board real quick, but we start to think about this kind of idea that if you take the measure of the arc and you divide it by the radius, you are telling me how many radians that angle is. In this case, it's 2 radians because 10 over 5 is 2. Yes? And maybe you've seen this more in symbols. Arc length is oftentimes s, radius is r, angle is theta. So theta equals s over r, or s is equal to theta times r. So you've probably seen one of those formulas at some point in your past. And so let's see if we can try to figure out one way to relate angles that we're comfortable, sorry, degrees that we're comfortable with, and radians that we hopefully get more comfortable with. Suppose that we take this angle and we wrap it all the way around so that it gets right back to the beginning. So in order to figure out how many radians that angle is, I need to know how the arc length, the blue, compares to the radius, the red, right? Is it 5 times as much? Is it 8 times as much? Whatever it is, that's how many radians this big angle is. Well, the blue, now that it's the entire circle, has a special circle word. What's the blue length called? A circumference. And what's the formula for the circumference of a circle? 2 pi r. So then the circumference of the circle is 2 pi r. If I take that and I put it in the top of my fraction here, the arc length is now 2 pi r. And that's supposed to be divided by the radius, which is just called r. Then what is the magical angle that corresponds to the whole revolution? It is 2 pi. So what you guys have just figured out is that 2 pi radians is the same as how many degrees? 360. And that is our fundamental identity that's going to relate degrees that we're familiar with to radians that I want us to become more and more familiar with. So we'll just show a couple of other numbers up here. I will show that at the top. Let's see. So if the whole thing is 2 pi, then how many pi's is this straight up angle? Is pi halves, right? Half of a pi. So we can run all the way around and get lots of familiar looking things. It all comes because 2 pi is the whole revolution. All right. And I think that is good. Last thing on this one, here are the integer radian points. So if you have, I just marked these before class, that's 1 radian, that's 2 radians, that's 3 radians. Why does this 3 make sense relative to this number? Pi is 3.14. Does it make sense that 3 radians is just a little bit shy of straight to the left? 4 radians is down here in the third quadrant, 5 radians, 6 radians, which is a little bit shy of the 2 pi, 6.28. Okay, any questions on radians? Okay, so hopefully that motivates this identity that we talked about. We said that 2 pi radians is how many degrees? It's 360. So 2 pi radians is 360 degrees. And we'll go ahead and reduce that by dividing by 2. And so we get 180 degrees is the same as pi radians. All right, so we'll turn to page 20. And if you were in my class last spring, then you got very, very familiar with this diagram right here. So we're going to fill in a few of these things. We've got a bunch of information on this page. You'll fill in most of it later on just to, again, kind of warm up your brain and get back into Radian mode. But let's just go ahead and fill in, let's fill in all the information about this guy right here. Okay, so I will tell you that the special angles that we've put here in the middle are at 30 degrees, and what's the next one? 45 degrees, and the next one, 60 degrees. And what I'd like to do is figure out how many radians that 60-degree angle is. So we'll just do this one calculation on the side. You might just already have memorized 60 degrees is equal to blank radians. But if you haven't, it's easy to figure out. You take your 60 degrees, multiply by pi over 180. Because pi radians is the same as 180 degrees. So we're just multiplying by a fancy form of 1 here. So what do we get when we reduce? With pi's in it. Pi over 3. Everybody okay with this kind of conversion? So we'll put pi over 3. All right, and the next thing we're going to do is fill in the coordinates of this particular point right here, which is on our circle. Now first it's a unit circle, which means the radius is how much? 1. So it just makes life easier when the circle has a radius of 1. And so I'm interested in knowing what the x and the y are for this point. So just to remind us, I mean, it's standard x and y stuff. We just need to figure out what those numbers are. Just looking at the picture, not even thinking about any trig stuff, what does it look like x is roughly if the radius is 1? Something about a half, maybe a little bigger. I don't know. It's hard to know. And how about the y? Close to what number? It's close to 1. It's almost at the top of the circle, and the top of the circle is 1. So we're going to get some numbers here with radicals in them, but like this, it should make sense that we're close to a half and close to 1. And so I will tell you that your choices for the coordinates of all these points, all 3 of these points in the middle, you don't have many. Your choices are the following. You can have root 3 over 2, you can have root 2 over 2, and you can have 1 over 2. Which actually, just to keep the pattern going, I will write as root 1 over 2. So root 3 over 2, root 2 over 2, root 1 over 2. Those are your only choices for the x's and the y's. Now I've written these guys in descending order, so the biggest number is up on top. And I will go ahead and drop down from this guy, another x, and from this guy, a final x. So I've got 3 different x's for these angles. And I promise you that the x values are some choice in that green list. So the first x, which green number do you think it is if these 3 are those 3 in some order? So the first one is root 3 over 2? First one is a half. It's the smallest one up there. So we'll go ahead and put 1/2 right there. And how about the next one? It's root 2 over 2. And the last one is root 3 over 2. So those are our x's. And I'll go ahead and bring these guys over to the y-axis, and I will tell you that those y values are the same green numbers, just got to get them in the right order. So how much is the one we're interested in at the top? Root 3 over 2. You okay?
Oh, I'm good, yeah.
Are we enjoying this review of Radian?
Yes.
Yes. Love. Okay, so you can fill in the blank with some more information. So you've got lots of blanks to fill in actually later on. But what I want to do now is just remind us of a couple of other facts. So we are about to start talking about sine and cosine and tangent. The x-coordinate is which one of those functions? Sine, cosine, or tangent? The x-coordinate is the cosine. So x is the cosine of the angle. And the y is the sine of the angle. And then the last thing to put in this page, let's jump over here to this top left stuff. It says positive and negative. So what it's looking for here is a list of which of the trig functions are positive and which are negative. So let's see, positive. So we said that the x is the cosine and the y is the sine. And if you just pick any old point, any random point out here on the circle in the second quadrant, which one of the numbers is positive? Is it the x for this point or is it the y for this point? The y is positive because we're up above. And the x is a negative number because we went to the left. Okay, so if the y is positive, I guess that means that out here, the sine is positive, and the x, that's the cosine, is a negative. So cosine is negative. And that's true for any angle that you pick in the second quadrant. The sine of all those angles is positive, and the cosine of all those angles is negative. Okay, but there are some other trig functions to think about. So let's start listing a few others. I will tell you that generally there's only one trig function that's positive in any quadrant. So the other 2 must be negative. So I said sine, cosine, tangent. What do you think is true about tangent in this second quadrant? Tangent is negative. And then there are three other trig functions that don't get the same love that these first three get. But you can fill in the blanks with secant, cosecant, and cotangent. The three that I've written up here are the three we'll be focusing on. But anyway, any questions on this? A lot of stuff going on this page. Okay, so then a big thing you're going to do tonight or tomorrow is fill in as much as you can and then check with your neighbors for a lot of data to fill in, but I think it's worth your time just to refresh your memory about all this radian and then sine cosine stuff. Good? Okay, so on the next page, I'll go to number 2. And can we go to Lindsay for number 2? Okay, thank you. So we're going to fill in. We've got a much more simplified version of our circle. We're going to fill in the blanks for each of these guys. One thing I'll point out, this is no longer a unit circle. The radius is some general r, okay? So what we said on the last page was that sine of t, is it the x or is it the y? Sine is the y. But now we need to bring the fact that it's not a unit circle into this guy. You guys know where the r goes? Is it r times y? That's right. R times the sine is the y coordinate. So if I'm going to move the r to the right-hand side, where does it go? It's divided by. So that right there is the definition of sine of t. It's the y divided by the radius. When the radius is 1, what does this become? Just y. That's why it's nicer when the radius is 1. Okay, cosine of t is x over r. Tangent of t. Yeah, so some people are saying something with sines and cosines, and others are saying something with x's and y's, and they're both good. I'm going to do the sine cosine version down at the bottom here. So let's just do x's, y's, and r's. So what is tangent? Is y over x. Okay, and then on the right-hand side, we have the three trig functions that we don't pay as much attention to, but if you write them in the right spots, then it's real easy to figure out what the x's and y's and r's are. What do we do to get from the first column to the second column? Flip it. So this cosecant is r over y. And you can flip the other two. Okay, so we've got our 6 trig functions all defined in terms of x's, y's, and r's. Now we'll take a step back. Probably before you did anything with x's, y's, and r's, you used SOHCAHTOA and hypotenuses and opposites and adjacents. Can you guys with your neighbors fill in some combination of those 3 words for each of these trig functions? Opposite, hypotenuse, and adjacent. Check in with your neighbors. Okay, how are we doing with the SOHCAHTOA version of things? Okay, splendid. All right, and then the next identities we're going to talk about are these things called quotient identities. So I have a shirt that I wear twice a year. So this is to help you guys. So what's the definition, or what's the quotient version of tangent of t? Is sine over cosine. So let's put sine of t over cosine of t. And cotangent of t is cosine over sine. And cosecant, is it related to sine or cosine? It's related to sine. Todd's got it. It's 1 divided by sine. And then finally, secant is 1 divided by cosine. All right, hopefully we're not feeling too overwhelmed yet. I know it's a lot of information. This is like 3 weeks of a pre-calculus class we're doing in 20 minutes. So hopefully it's stuff that we've seen and it will come back. We've got 3 Pythagorean identities. Anybody know the main one? Good. Sine squared plus cosine squared equals 1. For any angle t, sine squared of t plus cosine squared of t is 1. I said there were 3 of these things. I can never remember the other 2, so I always have to figure them out on the fly every time I need them. But to figure out the other ones, you could take everything in this equation and divide by cosine squared. If you divide by cosine squared, what does this first thing become? It's sine over cosine, which is also known as tangent. So if I divide this guy by cosine squared, it becomes tangent squared. Plus, if I divide this by cosine squared, what do I get? Plus 1 equals. And then we divide this one by cosine squared. Well, 1 divided by cosine is which trig function? The secant. So this is secant squared. And you get the other one by dividing everything by sine squared. So if you divide everybody by sine squared, you get 1 plus cotan squared is equal to cosecant squared. Okay, so that's enough identities, I think. There are plenty of others. There's like almost an unlimited number of identities. There, you have like double angle formulas, half angle formulas, sum and difference formulas. There's all kinds of identities you can play with. We've got what I think is a bare bones, good enough for us list of identities here. Okay, I'm hoping that you guys are comfortable with the graphs of the trig functions. At the very least, super comfortable with sine and cosine, a little bit familiar with tangent, and again, the other ones we just aren't going to pay as much attention to. So just a couple of relevant features of the cosine graph. Highest point is 1, lowest point, -1, middle is at y equals 0. The period is 2 pi, meaning this function repeats every 2 pi. And all of those things that we just said are true for cosine, and they're also true for sine. So really the only difference in my mind is that cosine, if I think of it starting on the y-axis, starts at the top, whereas sine starts in the middle. And so really that's like the only difference that I look at when I'm looking at a graph to decide if it's a cosine or a sine. Does it start at the top, or does it start in the middle? What if I wanted it to start in the middle, but be on its way down? You'd make it negative sine of t. Yes? What if I wanted it to start at the bottom? You make it negative cosine. So starting at the top, the middle, or the bottom, and going either direction, we can handle it by either making it sine or cosine or negative, one of those things. Okay, some more pretty graphs here. You'll notice that all 4 of the other trig functions have vertical asymptotes, so they look quite a bit different from the sine and cosine graphs. And we just merrily move along until we get to number 3. So we're on page 23. Okay, so in number 3, it says we're going to recall some basic facts about functions, well, basically just sinusoidal functions. That's what we call them. So I've got a sine b x minus c. And pretty soon we're even going to add a k here at the end. I don't know why I didn't put it in there, actually. Put a plus k at the end. And so the question is, what do each of these letters have to do with the shape of the sine graph or the shape of the cosine graph? So first, the number a. Anybody remember what it's called? A is the amplitude. And can somebody explain, without using the word amplitude, what is amplitude? Half of the magnitude. What's the magnitude? Super. Right? If you know how high it is between the max and the min, the total distance, amplitude is half of that. Todd, what were you saying? So it's how far from the midline to the top, or to the bottom. And that's the same as Joe's definition, or it's equivalent to Joe's. Okay, what about B? B has to do with the period. It does. B is equal to, there's a flow formula. That's good. Yeah, B has to do with how the graph has been stretched horizontally or compressed horizontally. And B is always given by this nice little formula. It's 2 pi divided by the period. I say always. I mean, it's true for sine and cosine because the period of sine and cosine normally is 2 pi. If you were trying to do something with tangent, this 2 pi would change. The period of tangent, well, this is a cotangent here, but what's the period of cotangent? It's pi. So this 2 pi over period would actually become pi over period. Again, we're mostly going to be doing sine and cosine. So this is fine. I'll just write in case you happen to want the other direction. If you happen to know what the period is and you want to figure out what B is, 2 pi over B. Okay, next we have C. Does C have to do with a vertical thing or a horizontal thing? It's horizontal. It's inside. It's near the X, so it's horizontal. We've already talked about the horizontal stretch. That has to do with B. C is called the horizontal shift. Yeah, counterintuitive. I'll write that. That's a good thing to remember. What do you mean by that, Abby? If C is negative, you move to the right. If C is positive, you move to the left. I've actually kind of built that in a sneaky way. There's a minus sign in the parentheses, but you're not going to have that in the problem you're given. So you just look at that number and you say, oh, if it's negative, actually to the right, which is weird. You think negative might be to the left. But everything inside is also weird, counterintuitive. And then what about this plus K? That's the vertical shift. Counterintuitive or intuitive? It's intuitive. If K is positive, which way? You move up. K is negative, you move down. Okay, so let's try number 4. We're going to graph this function, but again, I don't know why I didn't put a vertical thing in here. So let's put a -1 there at the end. So we're going to graph that function with a -1 at the end. So first we'll find all the relevant stuff: amplitude, period, horizontal shift, vertical shift now. What's the amplitude? Is it -3 or is it 3? It's 3. Yeah, amplitude is always a positive number. So the amplitude in this case is 3. The negative will flip the graph over, but it doesn't change the amplitude as a positive number. Great. Period. We'll use our formula here. The second formula we wrote in purple is 2 pi divided by B. 2 pi divided by what number? Divided by 2. B is the number in the front of the X. So the period of this graph is a single pi. We do. So first let's write down the wrong answer and then we'll update it with what Garrett has suggested. So according to what we wrote up above, the horizontal shift is that number, I guess we called it C. So what does it look like the horizontal shift is? It looks like it's a pi or a negative pi. Is it to the right or to the left? It's to the right. This is the counterintuitive part that Abby had said. Negative pi feels like you go left, but actually it's counterintuitive. This is to the right. and it feels like it's a shift of pi to the right, but it's actually not a shift of pi to the right, because that pi is going to change based on the updated period that we've got here. There's two horizontal things happening simultaneously. There's a smushing horizontally, and there's a shifting to the right horizontally, and it's going to be really important for us to be able to tease them apart so we can kind of write down each one's effects separately. And so Garrett's got the right idea. What we need to do before we write down what the horizontal shift is factor that 2 out in the front. So let's do that here. F of x equals -3 cosine of, factor 2 outside, and then there's a -1 that I added. So if we factor the 2 out of the first thing, what do we get? X, that's the goal. That's why you factored the 2 out, so it's just x. And then it's kind of weird to think of factoring 2 out of pi, but we can. What is there? It's pi over 2. And if you don't buy that, then just go ahead and distribute the 2 back through, and you'll see that 2 times pi over 2 gives us the pi that we had at the start. Yeah. So this is something we didn't necessarily recognize it when we looked at the formula, but yeah, it's written in a very special way where this b has been factored out in the front. And that's always what I do when I am trying to figure out what the graph is going to look like. So the horizontal shift is how much? It's actually pi halves. And we'll also point out that it's a shift to the right. Okay, and then finally the vertical shift. Yeah, so this is the k value that's sitting at the end. I'll say it's from +1, but I'll write the direction. Which way are we moving if it's a subtract 1? It's down. So we'll say 1 down. Mm-hmm. Oh, it's okay. Yeah, I mean, most important for me is that we get the graph right. So whether we say negative pi halves or positive, but say the word to the right, I want us to get the graph. And if we get the graph, then that's the goal. Good question. Okay, so let's see if we can get the graph. And I think getting the graph is still quite a bit of work. And I have my little way of running through. I have kind of a checklist in my mind of things to do to graph a trig function. And so you don't have to follow my checklist, but do it however is natural for you. Okay, so the first thing that I do is I figure out what the amplitude is. So we said the amplitude is 3. And so that means that normally the graph would go up to a maximum of what number? 3, and down to a minimum of -3, right? That would be our top and bottom. But it's not the top and the bottom because what other vertical thing is happening? There's a vertical shift where we go down 1. So if we go down 1 from each of these numbers, 2 and -4. So the first thing that I do is I put some dotted lines that are going to really cap my function. I can tell you without drawing anything that the graph is going to be entirely inside of that band. So up to 2 and down to -4. Probably a good idea to put the middle there as well. What's the middle? Is the -1. It's halfway in between. It's also that. It's also this vertical shift. So we'll put -1 as our middle. Okay. And the next thing I want to do is find our starting point. Now, the word starting point is really misleading because the graph goes forever left and right, so there's no start, there's no end. But for me, the start is unofficially the y-axis. Remember I had said you could start at the top or the middle or the bottom, so the y-axis is what I'm thinking of. And how far is everything shifted, in this case horizontally, is by pi over 2. So instead of starting on the y-axis somewhere, maybe normally it would start up there. Now I'm going to start it over here where I've gone pi over 2 to the right, something like that. So let's just start marking up our x-axis here. I'm going to go ahead and put pi over 2 as our starting point. We're going to start somewhere above or below that point. And the next thing I do is I mark the special x values from here forward. And this has to do with the period. So what's the period of this one? Is pi. So what I like to do is think of the graphs of sine and cosine. I'll just remind us here. I think of the graphs of sine and cosine as being 4 distinct pieces. 1, 2, whoops, try again. 1, 2, 3, 4. 4 pieces. And they go hand in hand with the 4 quadrants, right? So I always think of the graph of sine cosine as being broken up into 4 pieces. So what that means is that I like to think of these 5 points, and actually it means that you're taking the whole period and dividing it into 4 equal pieces. So what I always do is take the period and divide by 4. So we'll do this right here. Say period divided by 4. Always 4, because I always cut my graph up into the 4 pieces, the 4 quadrants. So the period divided by 4 is pi over 4. So the special points that I'm about to plot, these are going to be the top point, the bottom point, the middle points. Those are the special points for me. They're all going to be in intervals of pi over 4. But we don't start on the y-axis. Where do we start? We start at that pi over 2, the first point that we had plotted before. So we're just going to take this thing, I'm going to erase this in a second, but we're just going to bump over by pi over 4, pi over 4, pi over 4. And that's going to be one complete period, okay? So all I want us to do is find the x values at these bump points. So if we're going over by pi over 4s, maybe this is not the best way to write that fraction. Can I write that with the denominator of 4? Is it 2 pi over 4? So how about we update our update this starting point to make it easier to do all these calculations. So this is now 2 pi over 4. Is a better way to write the starting point of pi over 2. And every step to the right is a step of pi over 4. So what's the next one? 3 pi over 4. And the next one, don't reduce. 4 pi over 4. And the next one, 5 pi over 4. And then finally, don't reduce, 6 pi over 4. Those are the important x values for us. We had our starting x value, and then you just keep moving to the right by the period divided by 4. Okay, all that we have to do now is plot 5 special points. I'm looking for the points that are at the top, the bottom, and the middle. Okay, finally, I'm looking to see if this is a sine or a cosine, because up until this point, it didn't matter. Is it a sine or a cosine? It's cosine. Does cosine normally start at the top, middle, or bottom? Normally starts at the top if it's just a plain old cosine. This one is a negative cosine. So where does it start? At the bottom. So we're going to plot 5 special points. The first point is at the bottom, and it corresponds to the first x value that we've marked. So that guy right there is our unofficial starting point. If we're at the bottom, what's the next point that we're going to plot? Is it the top or the middle? It's the middle. And where does it happen? It happens right below the next x value that we marked. So that guy right there is the next special point. And there are 3 other special points. Can you guys plot them? Be careful as you plot. You match the right x with the right y. So we get our 5 special points. Every one of our points is going to be on one of those dotted lines. It's either the top, the middle, or the bottom. And every one of those points is either above or below one of the x's that we've marked off. And the last thing to do is connect them in some smooth way. Please, 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 after all the careful consideration you've given this graph, don't do one of these. That's not what cosine looks like, right? Cosine also does not look like this. What's the problem with that? Yeah. Okay, so first I was kind of sloppy. I missed the points in the middle. And somehow the concavity is always down. That's kind of strange. If I were to continue this graph, it looks like it's doing something like that. But that's not what it's doing. So even if you only draw the one period, you got to make sure you acknowledge that the cosine is about to repeat, which means it's actually quite flat coming out of this point, because we know it's just bottomed out. So very smoothly go ahead and connect our 5 dots. And that's the graph. Oops. So thank you. So graphing trig functions, it's a bunch of steps. I don't think that any of them are particularly hard, but it's just a lot of details. Any questions on any of that? And one thing I always like to do, and you guys are going to think I'm strange for enjoying this as much as I will, but what I like to do is I take out the graphing calculator and I want to check my work. So what we're going to do is we're going to type in this function in its original form right here. So you don't need to do this, but I always like to do this just to make sure I've got everything right. So it's -3 cosine of 2x minus pi, and then -1. And then before we hit graph, we're going to change the window, because what I would like to see is one complete period of this graph. And so I'm going to pick really special x values. What was our starting x value? That's 2 pi over 4. 2 pi divided by 4. What was our ending x value? Yeah, and notice it doesn't keep it. It changes right away to a decimal, but that's okay. So we go 6 pi divided by 4. What's the highest point? Or sorry, what's the lowest point for the y's? It is -4. The highest point? 2. And one last thing before we hit graph, and I really hope that people don't lose points on a test or a quiz for this. You guys most of you have physics right after this class. And what mode is your calculator in physics class? Is in degrees. That's super for TED. It will never do us well in this class. So it is going to be your job every day to decide whether you're in the right mode. So for all of calculus, we are in Radian mode. So anytime I hit any of these 3 buttons right here, sine, cosine, tangent, or the yellow ones right above them, inverse sine, inverse cosine, I first check the mode to make sure I'm in the right place. So if we hit graph, that's not right. If we hit graph, then we should see exactly one period starting at one corner, ending at another corner. It hits the top, it hits the bottom. It's just so pretty, isn't it? Isn't that just so nice? So that, what does it mean? It means we did it perfect, right? We picked a starting point, we picked an ending point, we perfectly, we've got like a real tight window going for this function, and we know everything there is to know about it. Questions on that? Okay, so let's take a look at number 5. And can we go to Tiffany for 5? Okay, so in your groups, can you guys come up with an equation that's going to describe this population of rabbits? And before I come up with an equation, personally, I would draw a picture. So take a look at the information in that paragraph, draw yourself a nice picture, and then see if you can pull the equation off the graph. Okay, so let's come back together and see how we did. So I've drawn a graph here. You might have drawn something a little bit different. Technically, this function says the t is the number of years since 2000, so 2000 is our 0. on the x-axis, and so the point that we had information about was -10. Probably isn't going to change much. So I plotted at -10, we were at the top, and at 0, we were at the top, so I guess we were at the bottom halfway in between, and I think that's enough info to get all the numbers. How much is the A? Is 1,000, which is how far it is from the middle to the top, or the middle to the bottom, or from Joe, half the difference between the top and the bottom. The B value has to do with the period, so we'll use Tony's formula here. He said it was 2 pi divided by the period. The period is given in this problem is how much? 10. That's how long it takes to get from one point to the corresponding point again. So reduce that, and we get B is pi over 5. All right, we'll come back to the C. The K value is the midline, the vertical shift. How much is it in this case? 4,000. All right, and then the C value, well, okay, so now we're going to decide, are we using sine or cosine? And you can use either one. Which one did you guys use? Cosine. Good choice. So cosine starts at the top, which is where this guy naturally starts. So if it naturally starts where it is, then how much is the horizontal shift? 0. So that's why we pick cosine. It would be good practice for you guys to try to write the same equation with the sine. And then more practice, write it with negative sign. You should have the flexibility to write it with any combination, any version of sine or cosine, plus or minus, but this is certainly the easiest choice. So then we'll bring it all together with our equation. So y equals, let's see, so it's the A value, 1,000. And is it positive 1,000 or negative 1,000 when I put it in the equation? It's positive because it starts at the top as opposed to starting at the bottom. Okay, you guys unanimously picked cosine. That's a good choice. What's the B value? We said pi over 5 times t. Normally it would be t minus something, but it's t minus 0 in this case. So we don't need anything else there. And then finally, plus 4,000. Any questions on that? Yeah, Chris.
Getting back to what Tony was asking, the amplitude helps the negative sign.
To be honest, I really don't care. I mean, if you say the amplitude is a negative number, I might write, hey, technically amplitude is always positive, but I won't take any points off for it. But more important than what we call the amplitude is what we call A. So if A is 1,000, you better put a positive 1,000. And if A is negative 1,000, then you put negative. The only technical detail is if you call it amplitude, it's technically a positive number. But like I said before, more important to me is that we get the graph. Okay, so we've got that. Let's move on to, yeah, Tony. Yes, K is always the midline. Yeah.
Rule about it was sometimes, but I think that was for sometimes for sine it worked or take the starting point. Take the starting point. Cosine it work.
Yeah, the horizontal stuff can be quite tricky because the shifting and the stretching kind of both impact the points, and so in order to tease them out, we do what Garrett had said, factoring that 2 out of the front. That's how we really identify what's what. You'll find a phrase, I think you'll find this phrase in your book, the phase shift, instead of horizontal shift. Phase shift is something that physicists and engineers and opticians and all those folks like to use. I'm never going to ask you for it because I can never remember what it is. And so I don't think it's fair to ask you to remember. Sometimes I think I've seen in some books phase shift is just the horizontal shift, but in other books I think phase shift is what fraction of the period you have moved, as opposed to a raw amount that you moved. And because I can never remember it, I'm not going to ask you to. So we've got our equation. Now we're going to use the equation in part B. Can we go to Bubba for B? Okay, so taking a look at this picture, I just want an estimate before we do any actual algebra. So we want the population to again be 4,500. So if you imagine this graph continuing over here, then I feel like at 4,500 it's somewhere down here. Maybe 4 years, maybe 3 years, I don't know, something, 2.5 years. So we've got some reasonable estimate for what the answer is. In fact, we probably could get even more reasonable. What is this number right here? That's the -5 there. So that means that the middle is -2.5, which means the next middle is at +2.5. Yes? Okay, so then, and 4,500 is above the middle. So something around 2 is what we're looking for. Okay, so let's see if we can do some algebra to get that answer, to get the precise answer. So we want the population to be 4,500. So let's rewrite our equation from before. You have to help me remember. 1,000 cosine pi/5. And then 4,000. Okay, so that was the right-hand side of our equation. Equals 4,500. Right? Okay, so this is the equation we're after. And we've estimated that the t we're going to get is going to be something around 2. Okay, I got a lot of things to move away from the t. What moves first? 4,000. So we subtract the 4,000 from both sides. And what moves next? 1,000 moves. What do we do with it? Divide. So divide both sides by 1,000. So that becomes just a half. Okay. Now, before we think about any fancy buttons on the calculator, the cosine equals a half is actually a nice angle. But we got lucky here. But a half was one of our special things, wasn't it? Where's our big picture right here? Here we go. Remember, the cosine, is it the x or is it the y? It's the x. And you want the cosine to equal 1/2. So you're looking for an x coordinate to equal a half. And we happen to have one up here, don't we? What angle makes the x coordinate equal to a half? Is pi/3. And I'm glad we didn't say 60 degrees. We do nothing in degrees here in calculus. So pi/3 is the answer. I mean, that's it. It's the answer. Well, it's one of the answers anyway. Where's the other point where the cosine is a half? Which quadrant? Yeah, we're looking for the same x value, so someplace down there in the 4th quadrant. You could find what that angle is too. So I've got those two basic angles, and then you could loop around as many times as you want and just land on one of them. So we're looking for pi/3 is the answer here. But let's make sure we can use the calculator to get it, because we got very lucky that 1/2 happened to be on our circle. If it had been 0.4, okay, it's not on the circle. So what do we do to both sides to get closer to t? Is arc cosine, right? So for folks who aren't as comfortable with the trig functions and undoing them, you might look at that and say, oh, divide both sides by cosine. Right? Looks like cosine times, but it's not. So what we'll do, I will just be really careful here. I will copy both sides exactly as they are. And then in the front of both sides, I will put the same thing. And the thing we put in is arc cosine, or inverse cosine. I'm never going to ask you to write that step, but until you're really comfortable with it, I'd write it. I mean, it's not some magical thing. You are doing exactly the same thing to both sides, and that's almost always an okay idea. And what happens on the right-hand side? The cosine and the inverse cosine cancel. That's why we did it. So what we have here is inverse cosine of a half is equal to pi/5 times t. And then the last thing, to solve for t, multiply by 5/pi. That's a good idea. Better than dividing by pi/5. Gets you there a little bit quicker, right? Divide both sides, or multiply both sides by 5/pi. So we'll just write our answer down here once. T is 5 over pi inverse cosine of half. Okay, so let's take those calculators out now and make sure we know how to use them to find this inverse cosine. All right, so from the main screen, first thing I want to do is just this inverse cosine of a half. So let's do that. So we do second cosine, 1 divide 2. Before you hit enter, what do you need to check? Your mode. We need to be in radian mode. Now we had said, the answer was pi over 3. Our calculator will never give us pi over 3. It will always give us a decimal, but we could double check because we happen to have gotten lucky here and gotten one of those real nice ones on the unit circle. But yes, it's the decimal for pi over 3. If I were in the wrong mode, if instead of radians we're in degree mode, the calculator is not going to say, hey, you're in calculus, you need to be in radian mode. It'll just give you a completely different answer. And unless you really know what you're expecting before you hit that enter key, you probably won't recognize that you're in the wrong mode. Now maybe 60, you'll say, wait a minute, 60 degrees, that's one I've seen before. But most of the time we get messy numbers whether you're in radian or degree mode. So be really careful. Everything this semester in this class is in radian mode. All right, and so then if I want the actual answer, I'll just type this whole thing in one shot. So it's 5 divided by pi, inverse cosine of 1/2. And again, the answer we expected was something in the neighborhood of 2. We thought it'd be about 2 years before we got to this number of rabbits again. And that looks pretty good. Questions on that? No, MathFrac is the only tool that we have, and it can't find the equivalent square root of something. And most of the time, if you're hitting an inverse cosine button, it's not going to be a nice fraction anyway. So we'll just have to accept some decimal approximation. Yeah, this one happened to be a nice one. Okay, let's come back to our real good picture down here. So we just figured out it takes 1 2/3 years for us to get to 4,500 rabbits. Yes? Okay, so we said that it was going to take about 1.7 years before we get to that number. But is that the only time when we'd be at 4,500 rabbits? No, there are many other times, right? We could get out here and just keep drawing, and we'll dip down, and then we'll come back up to 4,500. So why does the calculator not give you the one that's over there to the right? Well, the calculator needs to be consistent. And if I type in inverse cosine of a half, I don't want it to tell some of you pi over 3 and others of you 5 pi over 3, which is the fourth quadrant answer to this one. So there's this little technical detail that maybe you remember seeing from your pre-calc class, but I will tell you that if you type the inverse cosine on your calculator, the answer that you will get will always be between 0 and pi. It will never give you something bigger than pi. It will never give you something less than 0. We do that to make inverse cosine a function. So if you want to find another answer that's not between 0 and pi, you have to think about the graph. You have to use the symmetry of the picture to get the other answer. Calculator won't tell you. Similarly, inverse sine, if you hit that button on the calculator, the only answers you get will be between minus pi over 2 and pi over 2. So we're out of time for today, but there was just one other question I'd encourage you to just think about. I'm sure you'll see some in the homework. If you wanted to solve sine of theta is 0.8. If you type that on your calculator, you're going to get an answer that's in the first quadrant. You need to be able to use the symmetry of the sine graph to get the answer that's in the second quadrant, okay? So we'll leave that as an exercise. All right, so Wednesday we'll talk about derivatives of trig functions. Homework is in the usual place. Have a good Monday.